Hi all, I am K. Surya, working as assistant professor in the Department of ECE at SNS College of Technology. In this video, let us see about Modulo-N counters. A Modulo-N counter is a counter in which N represents the number of states present. M is equal to 2 power N, where N is the number of flip-flops required to design the Modulo-N counter. The modulo 6 counter, for example, has 6 states. So the value of n in this case is 3. That means the modulus 6 counter requires 3 flip-flops to be designed. Mod counters are cascaded counter circuits that count to a predetermined modulus value before being reset. Modulus counters are defined by the number of states they will cycle through before returning to their original value. For instance, consider a 2-bit counter that counts from 00 to 11. In binary, that is 0 to 3 in decimal, has a modulus value of 4, which is 00011011 and return to 00, and is thus known as a modulo 4 or mod 4 counter. It's also worth noting that it took 4 clock pulses to get from 00 to 11. Because of there are only 2 bits in the simple example, n is equal to 2, the maximum number of possible output states for the counter is 2 power n, which is equal to 2 into 2, that is equal to 4. Counters, on the other hand, can be designed to count to any number of 2 power n states in their sequence by cascading multiple counting stages into a single modulus or mod n counter. As a result, to count a single data bit while providing 2 power n different output states, a mod n counter will require n flip-flops connected. It should be noted that n is always a whole integer value. Next, we'll see how to design a mod n counter. So first step is to decide decision for number of flip-flops. So we have to find out first how many flip-flops are needed to design the corresponding mod n counter. So for that, we'll be using the formula n less than or equal to 2 power n. So consider you are designing a mod 10 counter, which is also known as a decade counter. So here the capital N value is equal to 10. And so we can find the number of flip-flops in the following method. So for example, you put n is equal to 3. So you'll be getting 10 less than or equal to 8, which is false. Next, put n is equal to 4. So you'll be getting 10 less than or equal to 16, which is true. So therefore, the number of flip-flops required is 4 for mod 10 counter. So we have to substitute n values in a trial and error method, and then you have to find out the number of flip-flops that is needed, which satisfies the equation n less than or equal to 2 power n. Next step is we will be writing the excitation table of the flip-flops. So here you're using a T flip-flop. So for T flip-flop, 0, 0 means 0, 0, 1 means 1, 1, 0 means 1, and 1, 1 is equal to 0. Next, step 3 is first we'll be drawing the state diagram and then we'll be writing the excitation table. So here we are having 10 states. So we are writing it from 0 to 9. So from 0 it will go to 1, from 1 it will go to 2, from 2 it will go to 3, from 3 it will go to 4, then 5, 6, 7, 8 and 9, and after 9 again it will go to 0. So these states are represented as 4-bit combinations because you need 4 flip-flops to design a mod 10 counter. So for 0 you represent it as 0, 0, 0, 0. For 1, you will be representing as 0001, and for 9, you will be representing as 1001. So in the truth table shown here, you will be representing this 9 states from 0 to 9 as 00002 to 1001. So if we see the first row of the truth table, so your state is 0, current state. Your next state will be 1. So 0, 0, 0, 0, which is represented as Q3, Q2, Q1, Q0. And the next state is represented as Q3 dash, Q2 dash, Q1 dash, and Q0 dash. So next state is 1 here. So 1 is represented as 0, 0, 0, 1. Similarly, you will be writing for all the 9, um, 10 combinations. And from the excitation table, which we saw before, you will be writing T3, T2, T1, and T0 by comparing Q3 with Q3 dash, Q2 with Q2 dash, Q1 with Q1 dash, and Q0 with Q0 dash respectively. So decade counter is also known as a divide by 10 counter, which counts from 0 to 9 and again reset to 0. So here 4 T flip-flops are used. So next we will be creating a Karnaugh map for each output T3, T2, T1 and T0 from the previous truth table. And you'll be getting the following expressions. For T3, it is equal to Q3 Q0 plus Q2 Q1 Q0. For T2, it is Q1 Q0. For T1, it is Q3 dash Q0. And for T4, T0, it is equal to 1. From the expression, we'll be drawing the circuit diagram using T flip-flops. This is the circuit diagram of T flip-flop. This is how a mod N counter is designed. So hope you understood how to design a mod N counter and how to find out the number of flip-flops needed for a mod N counter. Let us take up some assessment questions. What is the maximum possible range of bit count specifically in n bit binary counters consisting of n number of flip-flops? Yes, the answer is 0 to 2 power n minus 1. A decimal counter has dash states. The answer is 10. Thank you for watching this video.